Old people, what are you going to do? Okay, so that means that I need 50 newtons more in the direction of the acceleration than I have in the other direction. So if I've got 75 newtons back, I need 75 plus 50 or 125 forward. And that was review. That had nothing to do with the hard kind of friction, the static friction. And then we put that block B on top, and it had a static coefficient that was 0.8, and we were asked to find the friction that was acting on block B. Now, the first thing you were asked to do is draw a free body diagram for block B. The weight down was 100 newtons. The normal up was also 100 newtons because there's no acceleration up or down. The diagram has to screen balance. Now I've only got one more force in my quiver. Only one more force that I can put on that diagram, and that's the friction force by A on B. And because it's friction, it has to be parallel to the surface between A and B. It's got to be to the right or to the left or zero. Those are my choices. And I want this diagram to scream that acceleration. And I've only got one force left. So that friction force has to be to your right. Okay. Now that's one way of figuring out the direction of the friction force is what does it have to be to make my diagram scream what it's got to scream. Now there's another way. Maybe you could do this during the exam in the testing center. You let your fingers be the nooks and crannies between block A and block B. And then you ask someone to pull the rope, okay, pull it that way, okay, that's pulling block A towards the open door. And look what happens to the nooks and crannies of block B, okay, do that again. Okay, you see that they were pulled that way, okay, and that tells you. Now, if while you're in the testing center, you're asking people, pull my thumb, you're going to get in trouble. Okay, I'm just saying that's not called for. When I asked you how big that friction force was, many of us got it wrong, but no one's going to get it wrong today because you know the right answer. We talked about this on Tuesday. So everyone get the right answer and make me a happy guy. Okay, now you can click.
The brake stops. Static. It's acceleration.
Okay, last call. Is that all of us? Good, you remembered. Okay. So last day, and I'm here to tell you, when I put this on an exam years ago, most of the class got it wrong. And most of the class used that equation there for static friction. They plugged in the coefficient of kinetic friction, they plugged in the normal force, and they got 80 Newton. But that's not a formula for static friction. That is a formula for the maximum static friction, the point at which the block B slides off the back of block A. What that tells me is that I could get that friction up to 80 newtons before the surface breaks free. I could accelerate block A all the way up to 8 meters per second squared. And then block B would slide off the back. We're nowhere close to that. And 95, 99% of the time, you're not going to be close to that. And so what do we use to find that static friction? Well, that diagram has to scream that acceleration. How loud should it scream? F net equals ma. That's your most useful tool in your toolbox. That's gonna solve all of your problems in life. I did I promise that? That's not true, okay? That's not true. There's other problems. Okay, but I've got to have 10 kilograms. Oh, and this is also important. Some of my students got hung up because A and B were moving together. So in the mass, they wanted to lump it all together. 25 kilograms for A and 10 kilograms for B and make it 35. No, no, no. If that free body diagram is for block B, then the mass in F net equals MA is the mass of block B. Full stop, okay? And the acceleration is the acceleration of block B. And 10 times 2 is 20. That tells me that the friction force has to be 20 newtons. That's the scream it's provided by the friction force. Questions on that? Questions or concerns? Yes, sir.
Okay. So, specific questions, I noticed on some of them, you have like a net force. For example, the rope, each tree is pointing the rope, and there's no acceleration. How do we find the friction force again? Or how do we find that?
Oh, so like if I'm pulling one way and it doesn't go anywhere,
Yeah,
in that case, my diagram's got to scream 0. And so if I'm pulling with 400 newtons, the friction is 400 newtons. Now I'm pulling with 500 newtons, the friction is 500 newtons. You just got to make your free body diagram scream what it's got to scream. Question back here. On the test, there will be a formula for the maximum static friction, okay, with the max up there. Now, when do you use that formula? Well, there will be words in the question that will kind of telegraph that you're at the breaking point. Like, what's the greatest acceleration I could get block A to have before block B falls off? Or what's the hardest I could push block A before block B slides off? Then you're at the breaking point, and then you would use that maximum formula. But that rarely is the case. Okay. How many had fun with this problem here? Okay, this is Greg and his safe full of gold. I love this problem, not just because I've got gold, but because it's so rich. If you can understand this problem, all the other dynamics problems are a piece of cake. Okay, you've got Greg has a shop dolly with frictionless wheels, and he's using it to move a large safe full of gold. The mass of the safe is 875 kilograms. The mass of the shop dolly is 5 kilograms. Coefficient of static friction between the safe and the dolly is large, 1.5, so the safe does not slip relative to the dolly. Greg pushes on the safe with enough force to cause it to accelerate at 0.4 meters per second. Find the friction force between the safe and the dolly. Now, I'm not going to have you use your clicker because when you did this homework problem, you had different parameters, okay? You got different numbers. But I've got some numbers here that are commonly given for this problem. And I want you to notice something, and that is 2 newtons. Remember, a newton's a fifth of a pound. 2 newtons is such a small force, you're going to have a hard time feeling it, okay? On the other hand, 9,680 newtons is enough to crush you, okay? So if you get the wrong answer on this, it's not round-off error. There's something wrong with your free body diagram or your understanding of friction, okay? Because this is life or death. Either you can't feel it or it's crushing you, okay? So let's do this problem together. And again, as I'm doing this problem, think of this as all dynamics problem. follow this recipe. The first step in any dynamics problem is to draw a free body diagram of everything in the problem. So let's start with the safe. The first force I put on the safe is going to be the gravitational force. And that's going to be 875 kilograms times 10 newtons for each kilogram. That's going to give me 8,750 newtons. Okay. I then ask, are there any magnets? No, be patient. They're coming on Tuesday. Okay. So,
See you next week.
yeah, they're coming. What touches the safe? Well, I've got the Greg pushing to the right on the safe, and I have the dolly pushing up on the safe, and the dolly pushing back with a static friction force on the safe. Okay. Now I draw a free body diagram for the dolly. And I believe there's a better pen in here. The first force I put on that is the weight force, and that's a small weight force because it doesn't have much mass. And then I use Newton's third law. If the dolly pushes up on the safe, then the safe pushes back just as hard on the dolly. Okay, and I would use tick marks to show that they are third law companions. And if the dolly is pushing back on the safe with a static friction force, then the safe is pushing forward. I put 2 tick marks here. And finally, the floor is pushing with a normal force, but no friction because of those wheels. Yes, sir.
How do you determine that the safe has friction to the left?
How do I know that the friction force is that way?
On the left of the first diagram.
Okay. Well, there are several ways, 2 ways to be precise. One is with your fingers, let your fingers do the walking. And now this is the safe and this is the dolly. And so if I push the safe, okay, if I look at how my fingers bend, that's a force this way on the safe and this way on the dolly. Now, for me, the better way is to say, I want both of these free body diagrams to scream that acceleration. I've only got one horizontal force on the dolly, and this diagram has to scream to the right. And so if this force is to the right, by third law, this one has to be to the left. Okay? Now, yes.
Yeah, so now if you were, let's say he was pushing on the friction force would be a lot greater.
Be huge. Yeah, be huge.
Since he's pushing.
Yeah, yeah. Thank you for bringing that up. I'll come back to that in just a moment. Okay. Every time I draw a free body diagram, I get to use Newton's second law twice. In the y direction, okay, this is for the safe.
Yeah.
In the y direction, the net force has to be 0 because my acceleration is all in the x, it's not in the y. And so that means this diagram has to scream balance, which means that this is 8,750 newtons. And by third law, this one is 8,750 newtons. Okay? Now, in the x direction, again, F net equals ma. Well, I've got the normal by the Greg on the safe, and that's in the positive direction. I've got the static friction by the dolly on the safe. That's in the negative direction, and that has to equal the mass of the safe, 875 kilograms times the acceleration of 0.4 meters per second squared, and that equals 350 newtons. But you'll notice that that equation has two unknowns. I can't solve one equation for two unknowns. And so I just go to my other free body diagram. Again, in the y direction, F net is equal to 0 because there's no acceleration. Well, I've got 50 newtons down, the weight of the dolly. I've got 8,750 down. I've got to have 8,800 up so that all the force up equals all the force down. That's the easy part. Now we do the X part. I only have one force in the X direction, and that's the force I'm looking for, the static friction by the safe on the dolly. And that's going to equal the mass of the dolly times the acceleration of the dolly. And that's going to be 5 kilograms times 0.4 meters per second squared, or 2 newtons. So the friction force is 2 newtons. Now, folks, if I could go back and just point out that there's the correct answer, 2 newtons. Well, 350, we said, was the net force acting on the safe. If the friction is 2 newtons, and this diagram has to scream to the right by 350, then the push by Greg has to be 352. Okay, so there's the right answer. There's the net force on the safe. There's the push by Greg. These two humongous forces are the number you would get if you blindly plug into that maximum friction force. This is what you would get if you used this normal force of 8,750, and the bigger one is if you use this normal force. Neither one of those is correct. Okay, what I'm trying to say is that I will find all the different wrong ways to do this problem and put those as the distractors. So if you get a bogus answer like that and you see it on the test, don't feel warm and fuzzy. That's not an indication that you got it right. Check with your neighbor, see if your neighbor's okay with this.
Oh. I think you said actually. Like.
I think so. I wasn't thinking. But I think I feel pretty good. So,
Generally, that's.
no. I don't do it.
Are there questions? Now, this gentleman brought up a very important point. This force is so small because Greg is accelerating he's pushing to accelerate that heavy safe. And the friction is just bringing that little tiny dolly along for the ride. But if Greg had tied a rope to the dolly and was pulling the whole thing across, the friction force would be huge, because now the friction would be the only thing that's accelerating the safe. Good point. Thanks for bringing that up. Yes, sir.
Or when you're doing the friction or using the net force times it.
The mass is always in kilograms. Always, 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 every stinking time. Whenever you've got an M, you put the kilograms. Okay? Okay. Okay, let's move on. I probably should apologize. This morning, I thought that I would fix myself by squirting very high pressure water into my ears to fix them. It turns out that didn't help. Uh, I can't hear a thing, so I'm just watching your lips move. So I'm really bad at this. I need to maybe go see a doctor. I mean, I'm a doctor, but I'm just not a good one. It's not the right kind. Okay. Um, let's talk about Sir Isaac Newton. You remember he gave us the calculus, but the reason he gave us the calculus was because he was working on gravity. Okay. He was working on gravity. Now you remember there's this story about how he came about gravity. And it involves this diagram that we find in his notes. And this diagram depicts a very tall mountain where he thinks about firing a cannonball, perfectly horizontal. And he argues that the cannonball is going to fall at the base of the mountain. But if I fire it faster, it's going to get further from the base of the mountain. And if I fire it even further, the curvature of the earth is going to come into play, okay? And eventually, we're going to fire it so fast that it just keeps on falling and keeps on missing the earth. And we call that orbit. We get into orbit. This idea, and the speed that you'd have to go would be about 8,000 meters per second. That we call escape velocity. Now, this is not obvious. This is not something that everyone just knows. I went to high school in Guam, and my physics teacher had only had one physics class in his whole life. It was the equivalent of Physics 105. He was a marine biologist, and he was asked to teach the physics class because he had had more physics than anyone else at the high school. And I remember he came running up to me in the hallway one day, Greg, when things orbit the earth, they're just falling around the earth and missing it. And then he ran off. And I thought, oh boy, he just made that connection. We're in trouble. But he was a great advisor for our scuba club. I mean, he took us scuba diving, and in class, he taught us physics for about 20 minutes, and then he showed the best pictures of sharks ever. It was great. It was great. Okay. Now, we hear this story about the apple falling on Newton's head, and then suddenly, aha, gravity. That's not the whole story. Newton recognized that the falling apple was no different than the moon falling around the earth and kept on missing it. Okay, that they both were falling. He also knew that the acceleration of the apple was 9.8 meters per second squared, like we know. Okay. But he was able to calculate the acceleration of the moon using a formula that Galileo had given him. And we'll talk about that formula on Tuesday, not now, we don't have time. But with that formula, he was able to figure out that the acceleration of the moon was 9.8 meters per second squared, divided by 3,600, a lot smaller than the acceleration of the apple. He also knew that again, from Galileo, that the moon was 60 times further from the center of the earth than the apple was from the center of the earth. And suddenly he saw that 3,600 as 60 squared. Okay, that was the connection that he made. Now, the reason he invented the calculus was to prove that for a spherical earth, you could pretend that all of the mass was right there at the center of the earth. You didn't have to worry about this mass being closer to the apple and this mass being further from the apple. Okay, so that's why he invented the calculus. Now, with this realization that the distance depended affected the acceleration as 1/r², he gave us this formula. What he said was that anything with mass attracts anything else with mass. My head is attracted to that little 1 kilogram mass piece. We're going to find that that attraction is very, very small, small enough that we can just forget about it. Okay. But before we forget about it, let's look at this formula. Any two masses, the apple and the pear, M1 and M2, separated by some distance r, will experience a gravitational force equal to the product of their masses and divided by their distance squared, the distance between them squared. Now, this capital G is a constant. We call it the gravitational constant. And by constant, I mean it's the same throughout all time and throughout all the universe, okay? So how do we find that constant? Well, in theory, it's pretty easy. If I take 1 kilogram and put it 1 meter away from 1 kilogram, well, that's going to be 1, that's going to be 1, that's going to be 1 squared. If I could measure the force between those two, that would be that constant. And if I could measure it just once, I would know it for all time and in all space. But think about how hard that would be. That force between these two masses is so small. How do I measure something that small? Well, enter Henry Cavendish, okay? This is, I think, one of the most inspiring stories in all of science. I love this story, okay? This was 100 years after Newton gave us that formula for gravity. It took 100 years to measure that constant. And the way he did it was he studied wire, all sorts of metal wires. And he studied what torque it took to twist the wires. And I imagine, I may be just projecting here, but I imagine that he would come home to his father and his father would say, Henry, tell me again, what is it you do? Well, Dad, I study wire. I twist wire, different kinds of wire. Right, Henry. What good is that? Get a job. Get a job. Okay. Now, I think that that's the way it went because I was in grad school for 7.5 years. And we started with 2 kids and ended with 3 kids. We got 4 now. But anyway, every year I would do unspeakable things to earn enough money to get my children back to their grandparents. Okay. I'm not proud of this. But MIT does experiments on humans. And I needed the money. And so they pumped chemicals into me as a guinea pig. And I don't know what they were. I just know that I got $50. Okay. Now, one of those studies, a federal judge told the Army that they could not keep giving meals ready to eat to the soldiers unless they were tested for 6 months. And so they got 30 healthy young men and they brought us together and we had to eat nothing but meals ready to eat 3 times a day, nothing else for 6 months. For 6 months. Okay, at the end of the 6 months, they brought us all together and they said, we know you cheated. We know you had pizza. Write down in this book how many times a week you cheated and what kind of food you ate when you cheated. Now, there were 3 Latter-day Saints in this study, Meshach, Abednego, and anyway, the 3 of us looked at each other. It was, what? We could cheat? I mean, we had been faithful. I mean, my friend David Gibson was a professor over in the engineering department. He went to his sister's wedding in Delta, Utah all the way from Boston. And he took 2 great big suitcases filled with meals ready to eat because he wasn't going to cheat. Anyway, okay, that's beside the point. Whenever I brought my children to their grandfather, he always asked me, Greg, tell me again, what is it you do? Well, Dad, I'm studying instabilities in inhomogeneous plasmas. Right. What good is that? Get a job. Okay. Now, what good was it? Well, with that wire that he was studying, he was able to find the value of that gravitational constant. And this is how he did it. He set up a dumbbell system with great big granite balls on the end of a bar, and he hung that from one of his wires that he had spent his life studying. And then he brought other masses up nearby, and the gravitational attraction caused this dumbbell to twist ever so slightly. Ever so slightly. But Henry had studied that wire so that he understood how much torque it was going to take to twist the wire by that small amount. And he got a value for that constant that was very, very close to the one we accept today. 6.67 times 10 to the minus 11. You don't need to memorize that. You don't need to memorize that. Now, what can we do with that? Well, we could calculate the force between my head and a physics book. Okay, that's the old physics book that costs $250 that most people use in this class. If we separate the book from the head by 2 meters, then we can use that formula now to find the gravitational attraction between the two. If I plug in the constant that Henry Cavendish gave us, and I plug in the mass of the book and the mass of the head, and divide by the distance squared, I get a value that is teeny, teeny, tiny. 2 times 10 to the minus 10. That's 0.00000000002. Let's just agree to forget about that. Ignore that. But before we do, what is it really? Is it the force on the book, or is it the force on the head? Or do I have to cut that in half and give half to the head, half to the book? What do you think? It's the force on both. It shouldn't surprise you that Newton's law of gravity has Newton's third law built right in. Look, this is the force by 1 on 2. If I want the third law companion, I switch those indices, the force by 2 on 1. Well, 3 times 4 is the same as 4 times 3. So Newton's third law is built right into the law of gravity. Built right in. So that's the force on the book and the force on the head. Now, the forces that we care about are the forces exerted by the Earth, because its mass is big enough to make these forces considerable. Now, I know that the weight, the gravitational force of that book, is given by the mass times 9.8 newtons for each kilogram. We found that in class earlier, okay? But now I can use this formula that Newton gave us. But I need to know some things. I need to know the radius of the Earth. Well, it turns out that's not hard. I used to calculate that with the high school teachers that would come to my class every summer, just using a duck pond on University of Washington's campus, a 2-meter stick, and Mount Rainier on a sunny day. They would use the 2-meter stick and a little bit of trigonometry, similar triangles, to figure out the height of Mount Rainier. But that didn't take into account the curvature of the Earth. And so when they compared their answer to the true answer, and they knew how far away Mount Rainier was from campus, they could figure out the radius of the Earth. It wasn't that hard. What is hard is finding the mass of the Earth. 5.98 times 10 to the 24 kilograms. How do you do that? What scale do you put the Earth on? Okay, and is that scale riding on the back of a tortoise? I don't know. Okay, Well, here's how you do it. You do it Henry Cavendish's way. If I plug into that formula, there's Henry Cavendish's constant, there's the mass of the Earth, there's the radius of the Earth, the distance between the center and the book, squared, and there's the mass of the book. Everything in the red box has to multiply and divide out to 9.8. What that means is that if I know the mass of the Earth, I could have found that constant. But let's dance that backwards. As soon as Henry Cavendish found that constant, I know what the mass of the Earth is. It's whatever number I need to make this all multiply out to 9.8, right? So when Henry Cavendish measured this number, he knew for the first time what the mass of the Earth was. I imagine him coming back to his father, and his father saying, Henry, what good is it what you're doing? Dad, today I discovered that the mass of the Earth is 6 times 10 to the 24 kilograms. Until today, no one knew that. And now, only 2 people know it. Me and you, Dad. And I love you. Okay? I love you. I love that story. I like that. I like that. Okay? Now, anyone know who that is? That is Story Musgrave, and you probably also don't know his mass. It turns out to be 80 kilograms. And this is another picture of Story Musgrave floating next to the, what do we call that? The spaceship. Oh, I'm losing my words. Help, what? I can't hear.
Space shuttle.
Okay.
Station?
No, it's not the space station.
Shuttle.
The shuttle. Oh, thank you. Thank you. The shuttle. Oh, man. It's just a matter of time. So, what's his mass, people? Yeah, it's still 80 kilograms. That's the same throughout the universe, okay? That doesn't change. That's a constant. But what's his weight as he floats there next to the space shuttle? 0? 0? He's floating there. Is he weightless? Turns out his weight is 648 newtons. Whoa. Where did you get that, Greg? Well, let me show you. There's the Earth as seen from the moon, if you believe that we went to the moon. If your parents taught you that we did. Which of those circles represents the orbit of the space shuttle? Yeah, it's the white one. They don't go very far from the Earth. Back at Montana State, we had a space shuttle mission specialist, an astronaut on our faculty, Lauren Acton, wonderful gentleman. And I asked him one day, Lauren, how high did you go? He said, oh, not that high, just 400 miles, 400 miles, okay? Now, it turns out that the radius of the Earth in miles is about 4,000 miles. So in the space shuttle, they just go an extra 10% away from the center of the Earth. Not that far, not that far. Now, if I ask what's the weight of Story Musgrave in his bathroom on a bathroom scale on Earth, well, I would take the mass of Story, which is 80, and multiply it by 9.8 newtons for each kilogram and get 784 newtons. Well, if we look 400 miles above the surface, my gravitational field strength is going to be weaker, but not a whole lot weaker. It's going to be 8.1 instead of 9.8, okay? And now I can find the weight, the gravitational force, by taking the mass of Story times the gravitational field strength up there, and I get the 648. And yet the newspaper said, he's weightless. He's weightless. He appears weightless. His apparent weight is 0. And that's what we're talking about today, apparent weight as opposed to true weight. Now, if I take this bathroom scale and I stand on it, I get a reading. it is measuring a force. But the question is, what force is it actually measuring? If I draw a free body diagram for me, I've got my true weight, the gravitational force, can't change it except through diet and exercise. And I also have the scale. This is the true weight. This is the scale pushing up on me. If I look at the scale, it has a small weight force, gravitational force. If the scale's pushing up on me, I'm pushing down on the scale, and the floor is pushing up on the scale. Which of those 5 forces does this thing actually measure? Talk to your neighbor. Which of those 5 forces does this actually measure?
I mean, I agree.
I will give you a hint. It can only measure a force that acts on the scale. Okay, so it's got to be one of these 3 over here. Okay, which is it? Yeah, it's how hard you're pushing on that scale. How hard you're pushing on that scale. So, why do I trust it to measure my weight? Well, because of Newton's 3rd law and Newton's 2nd law. By 3rd law, this force that it's actually measuring is equal in magnitude and opposite in direction to this force, the scale pushing up on the bottom of the Greg. Now, if Greg stands here with 0 acceleration, then by 2nd law, this force is the same size as this force, which is what I was trying to measure. So indirectly, I'm measuring my weight. Now, we call this force the apparent weight. We call this force the true weight, or the gravitational force. Now, again, the true weight, we can't change except through diet and exercise. But the apparent weight, the reading on that scale, I can make that anything I want, okay? If I jump, I can make that huge, okay? And if I'm in an elevator, I can make that different than my true weight. So here's the summary. The apparent weight is just the reading on the scale that's beneath your feet. It's equal to the normal force of the scale on your feet. And for acceleration equal to 0, it's equal in magnitude to your true weight, okay? All right. Let's practice this in an elevator. This is harder in Montana because there's only a few elevators in the state. We're backward people. Okay. If I am traveling in an elevator at constant velocity, 0 acceleration, that could either be stopped or it could be 100 miles an hour. That's a constant 100 miles per hour. In both cases, my free body diagram would look like this. I would have my true weight. Let's say for Greg, that's 175 pounds, okay? And then this would be the push by the scale on Greg's feet. And if this is 0 acceleration, this diagram has to scream 0. So your apparent weight is the same size as your true weight. But if that acceleration for the elevator is up, and let's just pause to think about what that means. I could be going up to the 10th floor and speeding up, or I could be coming down to the lobby and slowing down. And if you don't have a window in that elevator or lights that light up, you're going to feel the same either way. Your free body diagram is going to have the true weight of 175 pounds, but the normal force by the scale has to be bigger than 170 pounds to make this diagram scream up. And so that means your apparent weight is bigger than your true weight. And you feel that. you feel like the floor is being pushed up through your knee. You feel like you just ate 5 Big Macs. Oh, I shouldn't have eaten so much for lunch. Okay, until you get to the 10th floor. Now, what if that acceleration is down? Well, now your true weight's still 175, but the normal force by the floor, by the scale on your feet, is less than 175. And you appear to weigh less. You feel less heavy. All of a sudden, you feel light on your feet. I could dance all night. Oh, this diet's working. Okay, until you get to the lobby. Okay. Now, how are you going to use this on an exam or on your homework? What formula do we have for apparent weight? And the answer is we don't need one. We have Newton's second law, and that's all we need. Let me show you. This is the type of problem you can expect on the exam. You're riding down in an elevator carrying a 20-kilogram package in your arms. As the elevator gets to your floor, it slows with an acceleration of 2 meters per second every second. What is the apparent weight of the package? How heavy does it feel? Does it feel? Well, let's work that together. Okay. So here you are. You know that I can't draw. Okay, let's give him 2 arms. Okay, and this is the package. Okay, and remember it's 20 kilograms. And you're in an elevator, and the elevator is moving down, but it's slowing down, so the acceleration would be up. And we're told that the acceleration is 2 meters per second squared in magnitude. Okay? Now remember, we need to ignore the velocity vector. That's never helpful. We want to concentrate on the acceleration vector. If I draw a free body diagram, the weight force, Earth on the package, well, that's just going to be 20 times 10 or 200 newtons. Now, I know that this normal force by the, let's call this the Greg. I know the normal force by the Greg on the package has to be bigger than 200 because this diagram has to scream up. Well, how loud should it scream? Well, that's given by Newton's second law. F net equals ma. We're taking a 20 kilogram package and accelerating it by 2 meters per second squared up. I need a scream of 40 newtons up. Well, in order for this diagram to scream up by 40 newtons, this has to be 240 newtons. And that's how heavy the package is going to feel while I am slowing down. Yes, sir.
You always want that in newtons, or will you ever want it in?
I can't hear.
You want it in kilograms or newtons?
Oh, it's a force. It's a force, so it's in newtons. It's always, all forces are in newtons. The only thing in kilograms are masses. Okay?
So we're just adding the force acting on the kilogram package, cause it to accelerate at 2 meters per second per second.
Yeah, that's one way of looking at it, but in truth, there's only 2 forces. There's not an extra force. There's just 2. And the upward force has to be bigger by 40. And I would call this the apparent weight. And this would be the true weight. This is how hard the earth is pulling on it, but this is how heavy it appears to be in my arms. Okay? How heavy it appears to be in my arms. Now, what if the acceleration is down and has the value of 9.8 meters per second squared? Okay. Well, that's free fall. Okay, and I know that my free body diagram for free fall is very simple. How big does that normal force have to be if I'm in free fall? Yeah. Did you see him? Did you see him go up? Isn't that clever? Wow. Yeah. The power of PowerPoint. Okay. Now, remember, that's how we recognize free fall, is because you have this very simple free body diagram. It only has one force on it. Nothing else is touching it. Okay. And so what's happening here? Is he weightless? No, his weight force is going to kill him in a half second. Okay. When he gets to the bottom. Okay. He's apparently weightless. He's falling at the same rate that the elevator is falling. And so they're not pushing on each other and they're falling together. They're falling together. Okay. He appears weightless, but he is not weightless. Now, you've all seen this movie, Apollo 13, and you remember this scene here.
Well, folks, as you can probably tell, the Aquarius isn't much bigger than a couple of telephone booths. The skin of the LEM in some places is only as thick as a couple of layers of tin foil, and that's all that protects us from the vacuum.
How did they film that? Do they have a room in Hollywood where they push a button and gravity turns off?
Did they do it on a large plane?
And you know the name of that plane?
747?
Oh, that's the number, but the name is more descriptive. The Vomit Comet. The Vomit Comet. Okay. And what they do is they take that plane up at a steep angle and then they just go into a dive. Okay. Now, some students from Montana State went on the plane.
The moment we would experience zero-G came closer. Not knowing what we were going to experience, some of us got nervous, but overall, everyone was excited. It was time. We were told to sit on the floor for the 10,000-foot climb. During the climb, we all experienced 2G. It felt exactly like the Gravitron at the state fair, except after 30 seconds, the floor would fall out from underneath your body and you would float up to the ceiling, bounce off of the ceiling to a wall or the floor, and just keep bouncing off things until the plane came out of the dive and started another 2G climb. This was repeated 40 times. At the very end of each flight, the pilot would simulate what it would be like to walk on the moon and on Mars. I have to admit, push-ups are a lot easier on the moon than on Earth.
So, how many times did you vomit on the Vomit Comet?
3 bags.
3 bags. Holy cow.
Too much information. Okay. Now, BYU students also went on the Vomit Comet, and this is their report.
Like swimming in a pool with no water, doing somersaults in midair, and flying like Superman.
It's so different than anything else you can ever imagine.
NASA puts the students through a week-long training to prepare them for the flight aboard the Vomit Comet, named because of the number who become ill while twirling and twisting in midair.
They start to float, they start to drift.
Pilot takes them up to about 25,000 feet and then goes into a steep dive. At a certain point, the passengers start falling at the same rate as the plane and gravity disappears.
Okay, so this is no different than if we took the elevator and had a great big old giant just chuck the elevator up into the air. Okay, suddenly you're falling, the elevator's falling, you're falling together. Have any of you been to the Tower of Terror in Disney? Okay, yeah. Fun ride that I never want to go on again. They put 13 people in this cage-like elevator. They take you up 13 floors through a haunted mansion. When you get to the top, they open up some bay doors so that you can see Orlando. And then they open up 12 more bay doors below you so that you can keep seeing Orlando while they drop you. And I'm here to tell you that when they drop you, you feel nothing under your seat but wet. Okay. Yeah. So, questions about parent weight before we go on to the next topic? Next topic's really quick. Okay. I'm going to introduce it with this funky Winker Bean cartoon. A lot of the other school bus drivers complain about kids fighting and fooling around on the bus. Phooey, I never have any trouble. If you go fast enough, they just stay pinned to their seats. Now, all of America laughed at that cartoon, but I don't think everyone was laughing for the right reason. Can you pin those kids to their seats by going fast? No. If they're going 100 miles an hour and it's a constant 100 miles an hour, they're going to not feel any different than in their living room. Okay? So the way you pin them to their seat is you've got to accelerate. You've got to accelerate. So let's talk about equilibrium. When I say I've lost my equilibrium, what that means is I've lost my balance. I've lost my balance. Now, those of you that are going to be engineers or architects, a whole lot of the problems that you're going to be solving involve equilibrium. Okay? And this is how we define equilibrium. An object's in equilibrium when all of the forces acting on the object are balanced. Zero net force. Another definition is something's in equilibrium if it has zero acceleration. And I hope that you see that by Newton's second law, those are exactly the same thing. Now, if you're building a house, you don't want it to have an acceleration, okay? And so that's why you solve a lot of equilibrium problems as an engineer or an architect. So, a rocket ship has lost all of its thrusters and is now hurling helplessly out into deep outer space at a velocity of 5,000 meters per second. Is this rocket in equilibrium? Yes or no? Yes, yes, okay. Here's another problem that we've seen before. Jeff is trying in vain to push a large freezer of elk meat. This is a Montana problem. A large freezer of elk meat across his garage floor. The mass of the freezer, including contents, is 250 kilograms. Coefficient of static friction between the freezer and the floor is 0.8. Jeff is pushing with a horizontal force of 1,000 newtons, but the freezer will not budge. What is the magnitude of the frictional force acting on the freezer? And you're given these formulas. They will be on the front page of your exam. Tell your neighbor what the answer is. Okay. I hope you told your neighbor it's 1,000 newtons. Because if it's not going anywhere, the free body diagram for that freezer has to scream balance, zero. And so if Jeff is pulling this way with 1,000 newtons, the friction must be 1,000 newtons that way. If Jeff's pulling with 800 newtons that way, the friction is going to be 800 newtons that way. It's that simple. It's that simple. Okay. Now, we had this pretest on Tuesday, and as I went around the room, I saw that most of us had correct free body diagrams, but not all of us. So let's talk quickly about the right answers to this pretest. Well, I asked you to put in your toolbox this suggestion. Always start with the free body diagram of the simplest object first. In this case, that's going to be the rock. Now you remember this was a crate with rough surfaces, nooks and crannies. This is a rock with rough surfaces, nooks and crannies, and we're pushing the crate at constant velocity across a rough floor. Okay, so if I draw my free body diagram for the rock, the first force I put on that diagram is always the weight, earth on the rock. I then ask, are there any magnets? No. What touches the rock? The crate. Does it push or does it pull? Not a string, not a thread, not a rope, not a chain. It pushes. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. Well, this is a rough crate and a rough rock. Shouldn't there be a friction force? Well, let's think about it. I've only got one force left in my quiver. I only have one more force that I can put on that diagram, a friction force. And the friction has to be parallel to the surface between the crate and the rock. That means if I put a friction force on there, it's got to point to the right or to the left, or it could be zero. Well, if I put a friction force to the right, that diagram's not going to scream constant velocity. If I put the friction force to the left, it's not going to scream constant velocity. The only option is zero friction. But wait a minute, Greg. You said there were nooks and crannies on the crate. You said there were nooks and crannies on the rock. Those nooks and crannies are intermeshed. How come as this thing goes across, they're not pushing on each other? Well, let's see if I can motivate that. When you're trying to decide if there's friction or not, I gave a suggestion. Grease down the surface and see how that changes things, okay? Now, if I grease down the top of that crate and I push that crate to start it from rest, the rock's going to slip off the back and break my toe. But that's not what we're doing here. We're not starting it from rest. We're moving it at constant velocity. So how about if I push on the crate and I push on the rock and I get them both going 5 miles an hour, a constant 5 miles an hour. And then I let go of the rock. What does the rock want to keep doing? A rock in motion wants to keep in motion at the same velocity. That's Newton's first law, Galileo's law, okay? And so even though this rock has nooks and crannies, and even though the crate has nooks and crannies, and even though they're intermeshed, they're not pushing on each other because the rock and the crate are both moving at a constant 5 miles an hour, and the rock wants to keep going at 5 miles an hour. The crate doesn't because it's got friction with the floor, but you're forcing it to by pushing the other way. Okay, so let's finish our free body diagram for the crate. I have the earth pushing down on the crate, pulling down on the crate. I have the rock pushing down on the crate, and I have the floor pushing up on the crate. I know there's friction fighting the motion, and I know for constant velocity, I must be pushing with a force equal to that friction. Okay? Those are the correct free body diagrams. Now, you were asked in that problem, that pretest, to find all the third law companion forces for any force on the rock, just the rock, not the crate, just the rock. Well, there's one pair right there. The crate pushes up on the rock with a normal force, and the rock pushes back also with a normal force on the crate. Now, that gravitational force on the rock also has a third law companion. The earth pulling up on the rock has a companion force of the rock pulling up on the crate. And that's on that messy free body diagram for the earth that we never really draw because there's too many forces. Check with your neighbor, see if your neighbor got this right. If they didn't, you need to slap them. That's the rule. Okay?
Let's check it out.
For the crate? Yes, but we were only asked to find them for the rock. Yeah. Yeah.
Oh, yeah.
I'll go.
Okay. In that text that I showed a picture of, the Cutnell and Johnson, that cost $250, there's this problem that I would assign every semester. It's this one here. A supertanker with a mass huge is moving with a constant velocity. Its engines generate a forward thrust of 7.4 times 10 to the 5th Newton. Find the magnitude of the total resistive force exerted on the tanker by the water and air, and the magnitude of the upward force exerted on the tanker by the water. every time that I assigned this problem, I was guaranteed to have a line outside of my office. And every person that comes into my office would say the same thing. We don't know how to start this problem. We have no idea where to start. And I knew as a parent, as a father, that every single one of those students was lying to me. Okay? They were lying to me because they knew how to start this force problem. How do you start every force problem? Free body diagram. Ding, 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 ding. 5 points for Gryffindor. Okay? A free body diagram. So let's draw a free body diagram. Okay? We have the weight down. I just took the mass of the tanker and multiplied by 10. We were told that there was a thrust force that was 7.4 times 10 to the fifth Newton. Now, they had never heard of a thrust force before. We'd never talked about thrust forces, but really it's not that complicated. As the propeller turns, it pushes the water back. By third law, if the propeller is pushing the water this way, the water is pushing the propeller and hence the ship the other way. It's that simple, okay? Now, we were told that there was an upward force by the water. We call that the buoyant force, and we're going to handle that later in the semester. It's one of the more interesting forces in nature. But we don't need a name for it to know that it's upward. We were told that in the problem, okay? We also were told that there was a friction force combined, some due to the water, some due to the air. I would never combine them like that. It wasn't my book. I would never charge $250 for a book, okay? But they did in the problem. But now I look at that free body diagram and I know what all the forces are. This tanker is moving at constant velocity, zero acceleration. This diagram has to scream balance, balance. And that means that this upward force, the buoyant force, has to equal 1.7 times 10 to the ninth. And this friction force has to equal 7.4 times 10 to the fifth. It's just balance. It's just balance.
So, what's the key characteristic of the situation that is?
Oh,
Like if you're reading the word problem, what is something that?
how do you recognize? Yeah, it will always have zero acceleration, but usually we describe it as constant velocity. Anything that's moving at constant velocity. Now, constant speed is not good enough because it might be going in a circle, but constant velocity is good enough. Now, folks, we've got 3 more minutes. Give them to me. We can spice this up. Oh, free body diagrams everywhere. I found it on the inner tubes. I'm going to get sued by Disney. Okay. Let's spice this up. Like you just pointed out, the most important words in this problem were constant velocity. That's what made it an equilibrium problem. But what if instead I said it was a constant acceleration? It's not a big acceleration, but it is something. Well, if I go back to my free body diagram, I didn't change the mass, so I don't change the weight. I was told that the thrust force stayed the same. Well, this diagram has to scream to the right, but it doesn't scream up or down. So that means this buoyant force did not change. The only thing that can change is that friction force. I need to somehow streamline this boat, make it more narrow, or get rid of some of the sails or something. Somehow get rid of some of the friction. Okay. Now, folks, this is as far as the morning class got because they're slow. Okay. Not as fast as you. So let's stop here and have a good evening. May the net force be with you, people. Bye-bye.